Hi everybody, I'm Olli Ahonen from IQM, and I'm here to talk about quantum computing today. I'll start with a few more abstract things like what, why, and how about quantum computing, and then we'll get to a bit more concrete things. And there's also a demo coming up. So, who am I? Quickly about me, I did PhD level research on quantum key distribution and quantum information back in the day. So I would say I'm a physicist by education, but I started doing software development things in 2008 when I joined Futurice. At least back then, Futurice was a really great place to work. So I really enjoyed the years at Futurice. I did mainly software developer consultant work, but also some other things around that. 2016, joined Zalando, then a startup called Kivra, 2018, and 2019 IQM Quantum Computers, as the company was just starting. So what do I do right now? I'm a product owner for a software development team, and what this team does is enable the quantum computers to be used for quantum computation. This may sound like a tautology, but it's not exactly that. So there's a lot of work to make the hardware work as an actual computer, a computing system, if you will. Alrighty, so what is this IQM? IQM Quantum Computers is a company that designs and builds and sells quantum computers. So it's a business that sells quantum computers. Established 2019 in Espoo, lots of people, more are coming in every day, and headquarters are in Espoo, and we have offices, well, all around Europe and soon elsewhere as well. Then the why question, why quantum computing? What is the idea here? The idea with quantum computers is that it will provide superior solutions for many, let's say, fields where you want to simulate or solve some computational problems. I've mentioned here a few, so things like molecular simulations, quantum chemistry in general, coming up with better fertilizers through this and so on. And then there's the optimization side. So you want to optimize your fleet of trucks or whatever. Some problems in there are very suitable for quantum computers, and you can achieve better results there. That's the idea anyway. And machine learning is everywhere these days, and it's also there with quantum computers. So there is the idea that machine learning will somehow benefit from quantum computing, but I put it here down as with a question mark. So let's see, maybe that happens. All right, and then how does quantum computing somehow outperform the traditional, i.e. classical computers? I have like two kind of intuitive ways of looking at it, and this is one of them. So in a classical computer, if you look at the very low level functionality, how does it actually work? It processes bits. So you have a number of bits there, and that's what the computer processes, ones and zeros. And very similarly, in a quantum computer, you have a number of qubits, quantum bits. How many of you have some kind of idea what a qubit is? Raise your hand, please. Okay, not too many hands. All right. A qubit is a two-level quantum system. That doesn't say anything to you, right? No, it doesn't. So basically, let's say to show or encode a qubit, you need two complex numbers arranged in a vector. So 1 by 2 vector, two complex numbers. And there are some normalization conditions. So that's basically what a qubit is. And the popular explanation is that it's 0 or 1 or a little bit of both. And that's also kind of true. Like if you really strip down all the extra from there, to represent a state of a qubit, you need two real numbers. So let's say two floating point numbers, approximately. And what does this mean? So let's take this example case. If you have 16 bits or 16 qubits, and we compare the classical and the quantum computer. So in the classical computer, if you have 16 bits, okay, so you have 16 zeros and ones, and this tells you the state of your computer, basically, the state of the computation. It's just 16 zeros and ones. But in a quantum computer, during your computation, you have this exponential computational space to use. So to represent this computational space, you would need more than 65,000 floating point numbers. And this is where the power of quantum computation comes from. At least this is one way of looking at it. So during the computation, you can move in this highly dimensional space and do things. whatever you want to do in your computation. The catch is, though, that in the end, what you get out from a quantum computer, it again needs to be classical information. So in the end, you really get, again, 16 bits of information. Each qubit will say, I'm a 0 or I'm a 1, and nothing else. So during computation, you have an exponential space to use, but in the end, you'll get 16 bits out. That's how it works. Another way of looking at it is through the physics. So what I have here on the screen is a state of a quantum computer. So that's a quantum state. And this state exhibits superposition and entanglement. And these are the two things that allow quantum computing to be more powerful than the classical computers. So superposition. Here we have 5 qubits. You can see 5 zeros and 5 ones there. And this state means that each qubit is in a superposition of a 0 and a 1 state. But not only that, they are also entangled. And this entangled means that they are either all 0 or all 1 at the same time. And that's entanglement. This is a maximally entangled state for 5 qubits. If it was not entangled, we would have 32 terms here with like 0001, 0011, and so on. And that would not be entangled. But now in this state, all the qubits are either 0 or all the qubits are 1. So those are kind of my 2 intuitive ways of thinking about where does this extra power come from. I bet there are others as well. Feel free to look them up afterwards. Okay, so in the why section, I didn't mention this integer factorization, breaking the encryption in the internet. It is still a very valid use case for quantum computers. You can do that, but you need a huge quantum computer. So millions of really well-working qubits, and then maybe you can break RSA. So we're not there yet. Where are we today? We are in the NISQ era. This is where we're today. Noisy. The computers have noise. There's lots of errors during the computation and in reading the results as well. It's intermediate scale. This means that we have maybe a few dozen, maybe 100, maybe up to 200 qubits. So the quantum computers are fairly small today, but they are quantum. This has been shown. They are actually working as quantum computers, so it's not a hoax. That's good. Another abstract concept before we get to the more concrete stuff is quantum advantage. So this is an important concept. Not the same as quantum supremacy. Quantum supremacy was demonstrated by Google. A quantum computer did something, whatever, no matter how stupid thing it did it faster than any supercomputer on Earth. So it outperformed a classical computer in some task. The task was completely silly. It was designed so that it will outperform on a quantum computer. So that's cool, nice, good achievement, but it's not quantum advantage. The point in quantum advantage is that the quantum computers do something that's beneficial to a business. So they solve a business problem faster, cheaper, with less energy, more correctly, more optimally, something like this. So when we have quantum advantage, then businesses will want to buy quantum computers to boost their own business further. We are, of course, at IQM trying to get there as quickly as possible, but as far as we know, no one has achieved this yet. Everyone is racing towards it. So before we get to the hardware, one more overlook of the scene. So not all quantum computers work the same way. There's a number of different technologies for making a quantum computer. Here's a list of them. And IQM is doing what Google and what IBM is doing also. So we are using superconducting technology. There's a chip inside the quantum computer. It's cooled down so that it starts to be superconducting in suitable places on the chip. But anyway, all these technologies do have the quantum promise. So they all have the same idea that they will be superior to classical computers. I also mentioned quantum annealers here. It's important to note that this quantum annealer approach, where D-Wave has already sold a lot of systems, it's beneficial for some simulations, but in my opinion, it shouldn't be considered a quantum computer. So it's more like a simulation test bed for a small subset of problems, where I'm sure it's useful for those, but it's not the same as a universal quantum computer, which is what these other technologies are trying to do. Then on to the more concrete stuff. Here's a drawing by one of my colleagues. It's an informal drawing of how IQM quantum computers look like. What's the technology there? What's the hardware there? So on the left here, you have, in this drawing, on the left you have the instrument rack. So this is full of microwave instruments. There are a couple of regular computers in there as well, direct current sources, all this kind of nice stuff. And what do? They send microwave signals into the cryostat, which is in the middle, and all the way down to the very cold superconducting chip that's there at the bottom. So it's like 10 millikelvin. So that's basically really cold. And that's where the stuff happens. It's a 1 centimeter by 1 centimeter chip there attached to the microwave lines. On the right, there are these crazy gas bottles. So that's what makes the thing go cold. That's the cooling system. And these are the like basic big components in superconducting quantum computers. So how do these actually look like in real world? They look like this. I am restricted to approved pictures that I can show in public, but don't fear, I can assure you these are all real pictures of real IQM quantum computers. Here we go. So this picture was published by VTT. VTT is IQM's paying customer, and we delivered this system to VTT. So again, this time on the right, you can see the microwave instrument rack. So the instruments are there, microwave coax cables going around, some other instruments, and there's also a rack server in there. In the middle, the white can, that's the cryostat can, and inside there is the chip. And behind there, you can again see the crazy gas bottles, which keep the system cool. This is from our lab in Espoo. So now the cryo can is open. Okay, the resolution in the call is not great. But anyway, there's this gold-plated chandelier there in the middle that you can see now that the can is open. On the left, you can see the side of a microwave instrument rack, and there are other quantum computers there in the background. Another picture from our own lab at IQM. Here you can see the cables which then attach to the superconducting chip. So all these cables carry a microwave signal or a direct current to the chip, to or from the chip. And finally, you need to isolate the system very well from the environment. So there are multiple layers of this thermal and magnetic shields then around the chandelier and the chip. Yeah, here's a picture of the chips straight out of the clean room. So that's a silicon wafer in the clean room. They put isolating things, normal metal things, and then things which become superconducting in the cold temperatures, such as aluminum or niobium and so on. And each one of those small squares there is a potential chip for a quantum computer. And then you attach it to this chip holder, and then you hook up the microwave lines and those. Neat. So that's the hardware part. Now let's get to the demo part. One of the questions is probably that, okay, so how do you program a quantum computer? Do you write some kind of quantum code? No, you don't. It's just Python. It's all Python. And now I want to share, let's see, another application. Here we go. So first of all, what is this thing I'm using? It's Jupyter Notebook. So this was new to me when I joined IQM. All the scientists want to use this thing called Jupyter Notebook. So it provides an interactive way to run Python scripts. And you can also do nice plotting with, let's say, Matplotlib or some other plotting library. So this is how many would probably actually use the quantum computer in a notebook, just like this one. So we can execute Python code here. Cool. What is this live demo about? I will now show how you would prepare and measure this highly entangled state for 5 qubits that I showed earlier. I did try to get us access to a real quantum computer today, but unfortunately, we don't have that many well-operating systems online at IQM at the moment, so couldn't find an available one today. But nevertheless, we can use the simulator, and it kind of shows the idea quite well. Right, so how do you do this stuff? We're importing from Qiskit. Qiskit is a quantum computing framework from IBM, not IQM, but IBM. It's very popular. I think it's the most popular quantum computing library there is. And from Qiskit, you can get a thing called quantum circuit. I initialized this quantum circuit with 5 qubits. And then there's a classical register of 5 bits for the measurement results. What do you do with this circuit? You add gates to it and measurements to it. And I'll show the output now, so it's a bit clearer. So you have the circuit. I add this H gate to the first qubit. It's a Hadamard gate. Let's not get into the details, but this is very similar to how you would view this regular logical circuit. So you have bits, and then you have gates that act on those bits, and then you can construct this. So time goes from left to right, and here you can see the 5 qubits, and then there's the classical register. And this is how you represent the quantum part of your quantum algorithm. This is the actual quantum computation, how it is usually modeled. So add H gate to the circuit, add controlled X gates to the circuit. Never mind what those do right now, but they are two qubit gates, so they involve 2 different qubits in the circuit. And then in the end, you want to measure all the qubits to find out their state. And this now, I happen to know that this will produce the highly entangled state that I mentioned earlier. So now we have the circuit. That's neat. Yes, this is a reminder for myself to check the auth status. Yeah, this tool is made by IQM, and now I need to log in again. Yeah, now I'm logged into our demo environment. So this thing is a testing environment specifically for testing stuff without access to an actual quantum computer. So it has the full software stack down to the driver instruments, but not the quantum hardware. So I can show you how it kind of works when you use a quantum computer, but we don't have the actual quantum execution today. Cool. Okay, so from the top again, what we need to do is to transpile the circuit. Why do we need to transpile it? When you have these generic circuits in your computation, these gates are not directly executable on an arbitrary quantum computer. So each quantum computer has a native gate set. In this case, the Hadamard and the CNOT gate, they are not native to the quantum computer that we pretend to use. So we need to transpile the circuit. Also, there's another thing. I'll show something from here. This is free and open source project by IQM. So you remember the two qubit gates here, okay? They involve 2 qubits. But in the hardware, in the chip, the qubits that are there, the so-called physical qubits that are there on the chip, which actually handle the physical computation, they are not all connected. So here is a diagram of the quantum computer we're pretending to use now. You can have 2 qubit gates between this qubit and this one, 1 and 3, but not between 1 and 4, for example. They're not connected. And this is always the case with quantum computers. The qubit topology is like a big thing. You need to transpile for that, and also the native gate set. This is the native gate set in circ terms for this quantum computer. So it's actually called phased RX, the single qubit gate, and then there's a control Z gate. Never mind what those are. They are just different from what we have in the circuit right now. So we need to transpile. Neat. Let's do that. However, to tell this transpile function, what are we trying to achieve here? The transpile function needs to somehow know, okay, so what is the qubit connectivity and what is the native gate set? And that's what we use this IQM's Qiskit adapter for. It's called Qiskit on IQM. Again, free and open source here. So we import this class from Qiskit on IQM, and then we can connect to our demo server, and then we can tell the transpile function that, yeah, this is the quantum computer that you want to transpile the circuit for. Good, now we have all the pieces. Let's do the transpilation. As you see, the circuit is quite different. So this is the original thing that we wanted to run. And this looks very different, or at least somewhat different. But it does the exact same thing. It is just a different representation of the exact same computation. So now we have transpiled the circuit. The R gate is a native gate, and these blue lines here are the control Z gate. Good. We have a circuit which is compatible with the quantum computer, and now we can get to running it on the quantum computer. But before that, we do what quantum computer users usually do, almost always, I would say. They first simulate on their local computer. So before using the precious quantum computer time, you want to have like a sanity check, smoke test maybe. Does this actually work? Does this make any sense? Am I doing the right thing? And these simulators are a big thing as well in the quantum computing community. Qiskit provides this one simulator. It's easy to use. Cool, let's use it. You just give the simulator the circuit and tell it how many times to run. This is also a big thing. How many times to run the circuit? You usually need to run the circuit many, many times. I'll come back to that. For the simulator, let's say we want to run it 1,000 times, and then there's just some processing of the results. What does our computation do? So what are we seeing here now? The distribution of the results, it is as it should be. So as soon as you ask one of the qubits, are you a 0 or a 1? It will say 0 or 1, and then the other qubits will also say the same answer. So it's either all 0 or all 1. Nothing in between. Good. We have done the simulation. This is all running on my laptop here. And now let's do the same thing on the demo server. So this is just like running on a quantum computer, except that the quantum part is unfortunately missing today. But never mind. We use the execute function, execute the circuit that's there on the demo backend, and run it shots times. That was 1,000. And then we process the results and so on. So as you see, now there are more options what comes out. And in the demo environment, the measurement results are completely random. You would also see this in a real quantum computer if it's not calibrated properly. If it's working a bit funny, this is what would come out. All kinds of different answers to the question. And even if it was calibrated well, this quantum computer, it would still produce a certain amount of all these answers. And this is what is then usually, well, almost always done with running quantum algorithms. So you want to run the circuit many, many times, 100,000, maybe even 1,000,000 times, to get a good distribution. So you would look at this distribution, and then the highest peaks would be the correct answer. In this case, there should be two very high peaks, the all zeros and the all ones answer. Right. If we had the real quantum computer access, it would look very similar to the thing that I was just showing. There's a URL for the server. You got a transpile for it first, then you execute, you get the results, and so on. So these are the basic building blocks that are involved when you're running things on a quantum computer. Then let's get back to the PowerPoint. Yeah, in the interest of time, I will skip a few slides and let's get straight to this one. It's a little bit small, but I can talk us through this. So this is what happens when you run things on a quantum computer. This is again the thing that I was mentioning there. There's the Python code that produces the circuits. You transpile the circuits, they go to the server. In our case, you have a circuit to pulse compiler. So it takes the logical circuit, compiles it to a lower level representation, which takes into account all the details, the calibration of the quantum computer. How do you actually execute those gates in the transpiled circuit on your hardware? So that's what the compilation step does. Then there's a low-level component IQM station control, which has the device drivers. We got to these device drivers all the way to that level in our demo execution just there. If we also had the quantum hardware, the drivers would be talking to these instruments. And the instruments would be sending microwave signals to the chip. Some of them would record what comes out, interpret those signals as zeros and ones of qubit measurement results, and those would be sent to the user's laptop. And typically, especially in these NISQ era algorithms, this loop would go on for a while. So you would send a batch of circuits for execution, see what comes out, look at the results, decide what to do next with your next batch of circuits, and run that, and then keep this loop up to find the answer to the problem that you're looking for. Depends on the algorithm how many times you want to do this. Cool. So that's how it works. Yeah, I have this bonus point here. So how do we do things at IQM? I thought this might be interesting to many Futurice people, since what I was doing before joining IQM was basically pure software products. It was always a software product, and it was basically following the SaaS model, so software as a service. The user didn't install anything in their own in their own computer, and well, maybe it was running on the customer servers, but still it was a SaaS model of delivering software to the users. But IQM is quite different. So we deliver the quantum computer with the control software to the customer's premises, and that brings like lots of different things to consider. So Sometimes the customer wishes to use their own server hardware instead of the one we provide. Okay, that kind of complicates things, but we can work with that. Of course, the customer has their own identity access management systems, monitoring, logging, backups, networks, all of these things bring a lot of kind of differences to pure software deliveries. And then there's the one thing that I mentioned briefly earlier is the calibration of the quantum computer. So the quantum computers, they're very finicky. They really are. You need to calibrate them again and again. It depends on the hardware a little bit, but you may need to do it maybe even once a day. Or if you're lucky, you can maybe get by with recalibrating once a month. But you need to keep doing that so that it produces correct results and the computation actually works. So that's also one thing. So you deliver the quantum computer to the customer, okay, but now someone needs to go in regularly and recalibrate the quantum computer, or it doesn't work. Another consideration. This is what somehow needs to be handled. All right, for you, where to go from here, this is what I would recommend. Introduction to Qiskit. Qiskit has really good introductory material and tutorials. They're hands-on. You get to write Python code immediately, run it on a simulator first. IBM also has this cloud quantum computing service, IBM Q Experience. I think you can run some things on a quantum computer for free there. So it's interesting to try it out. So it looks like this. Very easy to follow. There's like how to install, and then you get to looking at this stuff. It's quite well done. IQM, so us, we also have this learning material coming up, but it's not quite online yet, so I'm not able to advertise that just yet. Okay, that's it for today from me. Thank you.
Thank you. Do we have any questions online or in Helsinki? I have one if nobody else has anything. So where would you consider that Futurice could utilize this technology, or should we stay away from it?
I don't think you should stay away from it. I think it is good to, let's say, keep the door open for this thing. It might be that in 5 to 10 years, we will see something that this quantum thing really starts taking off with businesses. And at that point, it's good to have like the basics there to work with the technology.
I might have missed something, but I'd like to ask. So you said that you need to run the circuit like maybe 1 million times. How much does that take time in practice?
Yeah, surprisingly little. Good question. So let me bring up this diagram of the circuit. So these things actually work really fast. With our technology, the single qubit gates take around, I think, around 20 nanoseconds, and the 2 qubit gates roughly the same time. And then the readout is like less than a microsecond. So to run one circuit, you're talking about less than 1 millisecond. So it's quite fast.
Thank you. Another stupid question. The calibration you mentioned, it sounded like some kind of a manual task. What kind of a tedious task are we talking about?
Yeah, very good point. So the calibration is currently, I would say, it's very manual for most quantum computer companies. However, everyone, of course, wants to automate it. No one wants people to spend their precious time getting the quantum computers calibrated. So I think Google has also published some results that they have been really able to get this calibration quite automatic. And of course, we at IQM are also working on that. At the moment, it needs a lot of human to hold the algorithm's hand, but there are already steps towards getting it more automated. And for a 5-qubit quantum computer, it's totally doable manually. You need to run some experiments, look at some graphs, deduce some numbers. There's like a bunch of numbers you need, and that's your calibration. But when you have 20 or 50 or 100 qubits, it's not possible to calibrate it manually anymore. Then just things you need to check is massive. The calibration itself, it contains like thousands or even tens of thousands of values, so it needs to be automatic at that point.
Thank you.
I have a quick question. So when these things really kind of kick off and are kind of functional and easy to use and can be multiple easily produced, what is the kind of thing that's going to change our lives like hugely?
Yeah, again, very good question. So quantum computers are not very good for all kinds of things. If you want to multiply a list of floats together, for example, don't use a quantum computer, use a regular computer, it will do the thing faster. So the thing with quantum computers is that they're really promising for solving certain kinds of problems, but for all the other problems, there's absolutely no sense in using them. So how might this like look for like a layman who is outside the quantum computing community? I would think that there would be like an acceleration in these certain areas of optimization, and perhaps quantum chemistry would be one of the really promising ones. So we would see like accelerated innovation in perhaps fertilizer development or drug development. So you don't need to do the expensive lab testing. You can simulate how the molecules really work on a quantum computer, and then you would see quite a big boost in these businesses. I hope that answered your question at least somewhat.
Yeah, thanks.
One more.
So like in the example, we have the, so you're like translating the logic gates from the classical problem to the quantum bits, but how do you translate a real problem? Like how do you map that into a real problem, for example? Or
Yeah.
I'm not sure if that question makes sense. Or...
Yeah, it does. Yeah, I understand the question. That really requires some deep expertise, I would say. So currently, it's the physicist's job to figure this out. It's quite a complicated task to do that. So usually, what is done is that someone has already thought about the algorithm. Like, okay, yeah, this is how it works. If your problem looks like this, take these parameters and construct your circuits like this. So someone has already done the groundwork for you. You can just apply those ideas, and then this would be like the usual case for the execution.
Yeah. So like in practice, do you think how many qubits do you need to like have like meaningful to solve like a meaningful problem?
I would guess the number is around 200 to 300 really well working qubits. So that's another thing I didn't talk about. So the community talks about the fidelities of the qubits and the operations. So you can have a lot of really poorly working qubits, and that's pointless, or less qubits, but they work really well. So the fidelities are super high, and that can be more useful. But yeah, around 200 to 300, and then we start seeing some real benefits.
Thank you.
I guess related to that is, are you seeing some sort of a Moore's law or some kind of exponential growth in the amounts of qubits in quantum computers, or is it going linearly, or how do you see it?
To be honest, it looks more like linear at the moment. Yeah, getting the qubit count up is it's not easy. Like people are really trying to push, and it takes a lot of research and development to do that.
There's one more in the chat. So Martin Brolin asks, have you solved any high time complexity problems so far, which a regular computer couldn't solve?
No. Unfortunately, we are not quite there yet. So the regular, that is classical computers, they are still quite powerful compared to quantum computers, but the inflection point seems to be somewhere around 50 something qubits. So for some toy problems at that level, then you start seeing this effect that the classical computer cannot solve it anymore.
Good stuff. Thanks a lot. Ton of questions. Good stuff. Thanks a lot, Olli, and thanks everyone, and have a great weekend. And hopefully we see you all again when we have a next speaker for the Tech Weeklies. We have plenty of spots open, so pick one.
Thank you.